On a photographic plate from a telescope, two blue points sit side by side. Same color, same brightness, same quirks. A spectrograph, an instrument that spreads light into its component colors, shows the same pattern of bright lines in both, shifted by the same redshift, meaning the same stretching of wavelengths by the expanding universe. Then the first point flickers. Days later, the second point flickers in the same messy way, like a delayed echo. That shouldn't happen. Those points are quasars, the glare of gas falling into a supermassive black hole in a distant galaxy. Quasars vary unpredictably. Two separate quasars might look similar, but matching the same random flicker pattern is like two campfires that pop in the exact same order. So either the universe has staged an absurd coincidence, or one quasar is being seen twice. Empty space is not supposed to duplicate an object. A light beam doesn't normally split without glass or water. And even if it did, why would the copies arrive at different times? The trail back to the answer starts with a gamble made before any of these quasars were even known. In 1915, general relativity claimed that gravity is not a pull through space but a change in spacetime itself. Matter and energy curve the geometry. Objects follow the straightest possible paths inside that curved geometry. The unnerving implication was that light, despite having no rest mass, should also be guided by that curvature. Starlight passing near the sun ought to bend. That demanded a measurement. During a total solar eclipse, the sun's glare is blocked and stars appear close to the dark disk. If the sun bends their light, those stars should look slightly displaced. In 1919, Arthur Eddington's teams photographed stars during an eclipse and compared them to reference photographs of the same star field taken months later. The shifts were tiny, about an arcsecond, and the moon is about 1800 arcseconds across. But they were real. Gravity bends light. Once that was accepted, the next step was almost embarrassing in its simplicity. If a massive object can bend light, then a massive object can act like a lens. Einstein followed that thought in 1936. Put a foreground star exactly in front of a background star, and the bent light forms a ring. That ring is now called an Einstein ring. Einstein ended his note with a shrug. Such perfect alignments would be rare, and the ring would be too small to resolve. Fritz Zwicky noticed the loophole. A star is a lens, but a galaxy is vastly heavier, and a cluster heavier still. A galaxy could split a background quasar into images separated by a few arcseconds, wide enough for telescopes. Better, lensing would weigh the lens even if most of its mass was dark. Detectors and sky surveys eventually caught up. In 1979, observers found a quasar with a twin, two nearly identical points about 6 arcseconds apart. The first guess was a binary quasar, two active black holes near each other, but spectroscopy made that shaky. The emission lines matched like fingerprints, and deep images revealed a faint foreground galaxy in the right place to be the lens. At that moment, the puzzle snapped into focus. The twin quasar was one quasar, and the empty space between the images was not empty at all. It was filled with gravity. The intuition starts with ordinary lenses. Glass bends light because light takes longer to cross glass than air, so the fastest route curves. Gravity bends light for a related reason, except the slow region is spacetime itself. Near mass, time runs slower and distances are warped. Light still travels locally at the same speed, but the straightest path in curved spacetime can look curved on the sky. Put a galaxy between an observer and a quasar. Some quasar light passes the galaxy on the left, some on the right. If the alignment is good, both routes are bent toward the telescope, creating two images. With near-perfect alignment, a ring appears. With lumpy mass, 4 images can appear. The delayed flicker is the giveaway. Different routes take different times. One is longer and one may pass deeper through gravity, where clocks run slow. That extra gravitational lag is the Shapiro delay, a time delay caused by a gravitational potential. Add everything up, and one quasar arrives as multiple images with multiple arrival times. Take a 10-day delay. Light travels about 300,000 kilometers each second. One day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. 24 times 60 is 1440, and 1440 times 60 is 86,400 seconds in a day. Now multiply. 300,000 kilometers per second times 86,400 seconds is about 26 billion kilometers in one light day. 10 light days is about 260 billion kilometers. The Earth-Sun distance is about 150 million kilometers. So two paths that crossed billions of light years can differ by only about 1,700 Earth-Sun distances. That scale mismatch is exactly what lensing does, and it makes a sharp prediction. If both images come from one quasar, every intrinsic brightness wiggle should repeat with a fixed offset. Astronomers monitor these systems and build light curves, meaning brightness versus time records. The curves match, shifted in time, again and again. Then, lensing becomes a balance scale for invisible mass. Image positions and arc shapes reveal how mass is distributed in the lensing galaxy or cluster, regardless of how much light it emits. Applied to clusters, the required mass is far beyond what is seen in stars and hot gas, pointing to a dominant dark matter halo. The same physics connects scales. Radar signals that skim the sun arrive late, another Shapiro delay test. A single star can act as a microlens, briefly magnifying a background star. Tiny bumps in that brightening can reveal an exoplanet. Galaxy clusters draw giant arcs. And weak lensing, the subtle statistical stretching of galaxy shapes, maps the universe's web of matter. Lensing even measures cosmic expansion. Time delays depend on the distances between observer, lens and source, so they depend on the Hubble constant. With careful monitoring and careful mass modeling, lens systems can estimate that number. As of 2026, some lensing results favor a slightly faster expansion than the value inferred from the cosmic microwave background, the Big Bang's afterglow. This Hubble tension is an open problem. New physics is possible, but so are hidden systematics in the modeling. Dark matter itself is not a closed case. Small dark matter clumps inside halos should perturb lensed images, but stars can also microlens a quasar and muddy the signal. Separating those effects could reveal whether dark matter is cold, warm, or self-interacting. Upcoming surveys like the Vera C. Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope should find thousands of strong lenses, turning these rare curiosities into a statistical science. The paradox, one object showing up twice, resolves because geometry is allowed to do work. Light does not merely move through the universe, it draws the universe's curvature as it goes. If gravity can duplicate a quasar and delay its light by just a few Earth-Sun distances, what else is hidden in the distortions and time lags already written across the sky? Like, if this was interesting, hit the subscribe for more and turn that notification bell on.